Hi, welcome back. So in chapter 5, prediction by probability, the outline of univariate concept of probability to discuss the probability of a continuous value. And to emphasize the fact, and remind you with the map that we are actually following a path. Previously it was discrete, now it's continuous. That's why we are at this side of the map. And what we are working on is a probability kind of a model. Let's go ahead and actually explore that. I've tried my best to give a practical example where things can make sense. Imagine a certain machine producing kind of product in a space of time. Say the manufacturer is investigating that in interval from 1 to 4. X variable happens to be in minute. So this is a time interval, and we are trying to investigate the fact how much a machine is doing well in this interval. We decided to slice down the time, and then we observed how much a machine actually is doing well by counting the frequency of the total number of products are actually produced in that particular time. In the first interval, X could be larger than or equal to 1, but it's less than 2. In the second is larger than or equal to 2, but less than 3. Then larger than or equal to 3, but is less than 4. 20 products this machine is producing in this interval, then there's 50 in this interval, and 30 in that interval. The first question we might ask ourselves, something called the relative frequency, or the f of x. And relative frequency, it's as simple as counting divided by the total number of products the machine has produced in this interval time. Well, there's a 20% production in 4 minutes the machine will be producing in the first 1 minute. The same thing you could do in the second interval, and then you get 0.5 and finally 0.3. So these are workout probabilities, simple and in a form of a ratio. Now, what we want to do, we want to develop something called the relative frequency density, or the f of x, actually equal to taking the relative frequency here and divide it by the width of that class or that interval, because we are dealing with interval. We could take the 0.2 and divide it by 1. The 1 is the actually the width of that interval. The same thing here, 0.5 divided by 1. So all of them will be actually exactly equal in this particular case, so relative frequency. If we want to actually graph this, how about if we divide this interval into a smaller part, like say 0.5, 0.5. So in this case, imagine like we are actually splitting down this interval into 2 halves, and then we're investigating the frequency on each one of them. So imagine this 20 total, it becomes 5 and 15. So we've got all the relative frequency of x. And if I want to graph them, it's the same thing. You could see it's much more dense. How about if we cut that interval into a smaller pieces until you get actually finally curve would look like maybe this. Now, this guy here is called the probability density function, particularly well to be fit with such a continuous kind of variable. And if you sum the smaller pieces, 0.05, 15, 0.23, all of them, it will sum up to 1. That's why the entire area here, it should be equal to 1. And usually to capture these small pieces as we did by sum them up, we cannot just use the summation in mathematics like that, because this isn't a discrete. This is where we need to use actually an integral. Integrate from this minus infinity side to the infinity, given that the f of x, which is actually the relative frequency density we captured here, we have to integrate that in terms of the x, and all of that will absolutely equal to 1. So the area under the curve represents the probability, and that's why the total area here, it should sum up to 1 as we saw here. The second thing you have to also visualize is giving 2 points under the curve, say from A to B. We want to capture the probability from A to B, the area under this particular region. Decide the probability we're trying to capture of x larger than A less than B, which is going to be again the integral, but this time instead of minus infinity to infinity is going to be from A to B, and then you got the f of x. The last thing I would like to say, that the probability of f of x should be larger than 0. This is what you have to understand the difference. So in the previous discrete we were able able to say the probability of getting 2 or 3 because they are discrete. But here in a continuous, whenever I give you a specific value, if x happens to be continuous, then the probability in this case, it must be 0. Now, what we're going to do actually next, getting a real example, we have a random variable, okay, let's call it x variable, and has a probability density function known by this linear equation, say k multiplied by 2x plus 3, interval of x between -1 and 2, and it's going to be 0 otherwise. You are asked actually to find what is k. I don't want you to imagine that as a university exam or a class to learn how to solve the problem, but I want you to imagine, first of all, ask yourself, how do we reach up to this probability density function? How did we establish such a model? Well, it could have been many cases. Imagine this is a factory, a machine, a weather condition, whatsoever. And after a frequency of happening things, we came up to find out that in a certain interval between this -1 and 2, you can model the outcome to be in this form, 2x plus 3, scaled by this k number, whatever. And you are asked actually to find the real value of k in this case for some reason. Solution should be from mathematical perspective. That is an integral, since it's a continuous interval. And it's going to be from -1 to 2, f of x. The f of x is just given to me here. And I know the result or the area under this probability should be equal to 1. Learning how to integrate that. So the real value of k in this case is going to be 1/12. Let's try to get here graphing perspective. This is a linear problem. And maybe k is not important to be learned at the moment because it's just a scaling. So whatever the value of this line is going to be scaled by the value of k. First of all, take the value of -1 and fit it inside here. You will get some value here. Let's call it -1 in k number. And if we graph 2 here, so you will get at 2, you get 7k. What we know is that the area under this, it's going to be equal to 1. That's a trapezium from geometry perspective. When we know the area of trapezium should be half multiplied by the height here by the width. If you sum all that together, is going to be, should be 1. K is going to be equal 1/12. So it's exactly identical from visual perspective. Hope the idea is clear. Let's take one more actually example that involve not only one area, I mean multiple areas. It's not always linear. Take this example, a random variable x, and let's has a probability density function of x. And you could see there are 2 intervals here. The first seems to be quadratic function between -1 and 1, and then you got the second one, 1 and 2, and seems to be constant 107 and 0 otherwise. We want to find the probability of x to be, for example, less than or equal to 0. And also maybe a probability of x to be fallen between 0.5 and 1.5. Since I prefer always graphing, let's go ahead and graph the problem, right? The area under this, it should all sum up to 1. But let's now break down the question here. We say the probability of x to be less than or equal to 0. Well, less than or equal to 0, this is my 0 here. And I'm trying to find out the area from here to here. Well, this area is covered by which part of the f of x? Well, it seems to be covered with the first interval only with this. Directly you could say, well, the probability from -1 all the way to 0, and just take the integration of 4 minus 3x squared. You get the area of 3,7. So the area here is 3,7. Let's take the second part of the question here. X will be larger than or equal to 0.5, less than or equal to 1.5. It's more interesting because we're going to join 2 areas. 0.5 is somewhere around here. 1.5. So what we're trying to find actually, it is this area here. First of all, you could see that we've got 2 different areas. The first one, let's try to drop from the edge of 107 here, 107 here, and the other one is the other region here. This region is covered by the 17, and the second one is under this curve here. Let's take the first area, and then we're going to integrate the 4 minus the 3x squared in terms of the dx. Plus, now the second area, how to take it, we need the area of this rectangle. The width by the height is just a rectangle. Final area to be, I think, something like 13/56 or something. Now, what we're going to discuss next, and we have mastered the idea of understanding probability density function, and it's different from probability mass function, cumulative distribution function, the CDF. And the cumulative distribution function is something as a concept, it's valid for both discrete and continuous. And now things will make sense when we actually discuss that. That's exactly what we're going to do next. I'll see you then.